All right, good evening. So I'm getting really frustrated here because DigitalMicrograph won't stay open. And then I'm having to boot it up again, and then the share is getting canned when DigitalMicrograph crashes, and then I'm forgetting to tell it to share again, and then I'm trying to figure out how many minutes did I go in, before I didn't record what I was doing. So this is really, really frustrating me. I don't know why DigitalMicrograph is having such a problem here. This is not an online version, and I'm having it do things that are really not that difficult, and yet it's causing me a pain. So hoping we can finally get through this here. All right, so this is the spectrum image data that I took from the STEM-EELS tutorial a few months ago. Okay, so we're going to do some deep dive analysis into this, and I'm going to show you some of the additional things you can do. Okay. So if you don't have a copy of DigitalMicrograph offline, you can get one for free, and then you can process your DigitalMicrograph data on your own personal computer. Fairly easy to get, so I would encourage you to do so. And another useful shortcut in DigitalMicrograph when you have a lot of windows open is the auto arrange. And again, this is on version 3 point something. Okay, so if you do Control L, that will auto arrange your icon or your windows here. We only have one, but right, depending on where I have it, it will, in this case, it expands it the full size of the window. Now to see the settings for this, right click on Workspace, auto arrange, and you can tell it how to auto arrange. So I have it just on default, which is auto arrange and maximize. Okay, you can have it cascade, you can have it do a grid, you can have it pull up this dialog box every time you tell it to auto arrange as well. So a lot of options here, but just a very useful thing to be able to do. Okay, all right, so this is the spectrum image data set, and it's got 4 parts over here. Okay, so the interesting ones are the last 2, but we'll talk about these other ones quickly first. So scan, this is the signal that was being collected simultaneously with the spectrum image data. Okay, so you can see this is 256 by 128, which is the same dimensions as the spectrum image, and this was the head of STEM detector signal. Okay, so this is a head of STEM image that is perfectly coincident and correlated spatially with my spectrum image data. Okay, if I make a little adjustment over here to the gamma, I can see the layers a little better. So this is carbon up here, followed by an oxide, silicon dioxide presumably, and then we have epitaxial silicon germanium, and then a silicon substrate. Okay. And we can leave that on for now. If you want to pull this image for later, actually, let me turn this off here. So you can click on it, go to edit, and then duplicate. And then you can actually save this as an image. And then if you want to put a scale bar, right click, layout, add scale bar. You can do this for all your images. Okay, you can change the size. If you expand this more, it will change the name. Yeah, it will change the actual number. So this works pretty neat. You can move it around. If you want to close a window without saving it, hold down Alt. Okay. Another useful thing, you can digitally zoom with the scroll wheel here. Okay. And then if you want to drag the image around, right click and then grab the hand and you can drag it around. Okay. And then if you scroll wheel out, okay. But now it's a little tricky to actually get this back to the proper to being expanded to fill the whole area. Okay, so if you just do this, it doesn't work. If you do Control L, it doesn't work. If I expand it here and maximize, it doesn't work. So the shortcut here, if you throw this off, is double left click. And there we go. Okay, so it took me a while to figure that out, but that's how you center if you've dragged it off like that, double left click. Okay, all right, let me switch back to the pointer and we'll go to survey and I'll do Control L. So when you set up to take a spectrum image in DigitalMicrograph, you have to do it from preview mode. Preview mode is 1024 by 1024 with a 16 microsecond pixel dwell time. And so whatever was in the survey or the preview window when you tell the system to start collecting the spectrum image, that is what is going to show up here. So this could be in the middle of the scan. It could be after a scan is finished. It doesn't matter, but you will see this spectrum image box on here. And also if you had something for drift correction, which we didn't actually do when I took my spectrum image data in that case. Okay. Same thing. If you want a copy of this, edit, duplicate, and then you have it right there. All right, now the interesting stuff, EELS low loss and EELS high loss. Let's talk about the high loss first. So if we, what we're seeing right now is actually a slice or a window inside of the EELS spectrum, okay? And that's done pixel by pixel. So down here where you have slice, that's what this is. Okay, I'm going to change this to center so it's plus or minus this number, the width of the window. I'm going to make this plus or minus 25 about. Okay, and this is where it's centered. Okay, so this is useful for well, with the high loss, there's a few things we can do, but if we want to see how this works with regards to a spectrum. So if we want to generate a spectrum, left click and drag while you hold Control, and you'll open up the picker tool. If you hold Shift, that will make the tool or the box a square. Okay, and then if you want to knock it loose to make it a let's see how does, yes, there we go. You have to hit Shift again, and that will, again, hold Shift to make it a square, sorry. And then if you do it again, it will knock loose and become a rectangle, okay? All right, so there we're seeing the spectrum. So each of these pixels has a spectrum, a low loss and a high loss associated with it. And we're seeing now the sum of all of those spectra over this area, okay? This is specifically the low loss spectrum here. Okay, so if we come over here to the technique manager and analytical, so we can do a few things here. So if we, if I left click and drag, I can move this around. If I hold down Control, I can expand and contract my energy axis or my counts axis. Okay, if this gets thrown off, right click, layout, sorry, display, home display. Okay, that's a quick way to do that. Okay, but over here in slice, I'm going to click, sorry, show range. Okay, so now this is the range in the low loss spectrum that is contributing to my image up here in EELS low loss. So I can make this, let me filter this. And so basically I'm selecting only the ZLP right now. So this would be a zero loss image, okay? Zero loss filtered image, okay? And if we look next to it here, we see a Plasmon peak, okay? So let me actually move this slice over, make this a little bigger. So we're seeing right here, okay? So based on this, right, where I'm brighting, or where it's bright, I'm getting a strong Plasmon signal. So if I move this down, you can see as I go into the oxide, the peak moves over, and then now I'm into the silicon. Yeah, so you can see right there, if I make this fairly narrow, okay? Okay, so I don't see anything up here, but I see when I'm into the epi layers and the silicon substrate, okay? So same thing, if I move this back over here, I see bright up here because that's where I have the carbon and there's a shift with the silicon dioxide. The silicon dioxide is right about there. But there's also silicon there as well. So yes, this is a way to see where your Plasmon signals are coming from as well. We can also home the, well, actually I won't home the display. I'll just drag this down because I'm seeing the low loss here, which is all I need to see. Okay, so over here in EELS analysis palette, if you click zero loss, This is telling us the full width half max of the ZLP. And then if you want to know the thickness from the pixels integrated in here, click thickness, and it's telling us, okay, this is in terms of mean free path or lambda. And so this is good. We're well below 1, well below half. So 0.25 is generally very good as far as a relative thickness for doing EELS. Okay. And so now that's just for this area, right? And of course, I can make this down to just one bitty pixel here. So actually, let me digitally zoom in here so you can see, right? That's just one pixel at that point, okay? So, do this home display. There we go. Okay, so let me double click, there we go, to send it back. All right, so now if I wanted to get a thickness map, that's very easy to do. Okay, let me close this guy. And all I have to do is activate EELS low loss, come over here to thickness and push thickness. And I've got an EELS relative thickness map, okay? If I right click, layout, add intensity bar, so this is telling me the range from black to white. If I do a little, let me minimize this. If I do a histogram here, I can do Control H, and you can see where most of my pixels lie in terms of mean free path. So I got an average around maybe 0.27, which again is very good. One thing to keep in mind is that how it's setting the contrast limit. So if you do Control D and go to contrast, you can see what it's making peak black and peak white. So you can see even with the estimated values, I'm getting a little clipping. So these may not be the actual max and min. If we wanted that information, what we need to do is actually come up to Analysis, Statistics, and Min and Max. And we can see what those actually are. So if we come back to the image and do Control D, we can do 0.118 for the min and 0.397 for the max. Okay, we can see there's a little bit of a change there. I find it's helpful here to change this to a color map instead of grayscale. So Control D, color, and there's a bunch of options here. My favorite is black body extended here. That looks really cool, I think, and that really helps to show the variations, right? And so again, this is the full dynamic range of the image with no clipping. And so down here in the data bar, you can actually see what the value is at each pixel. Okay, so that is a relative thickness map. Okay, let's see here. Close this, and now we're going to get to the high loss, which is more interesting here. So the same thing, right, where we saw the slice on the spectrum, we can do that with the high loss. What this is useful for with the high loss is actually to help us find core loss edges here, okay? So if we come down to the slice here, I'm again going to make my width plus or minus 25. Okay, and then show range. And now what you're looking for here is as you move the slice along the energy axis, you're looking for spikes in the intensity. And when you see that, that generally means you've hit a core loss edge. Okay, so right what we're seeing here is boom, there's your silicon L23. Okay, now it's not going to, whatever we have up here is what's going to show up down here in terms of the spectrum. So we can actually, if we integrate this, it's going to be covered by red, but we'll still be able to see this. And actually, let me clear all these for now so we don't actually know what we're expecting to see just yet. Okay, and then we can drag this through, and then we're expecting to hit carbon next. And right about there, we hit, yep, so the carbon layer gets a little bright, and then we'll hit oxygen. And there we go, that gets a little bright. And then the last thing is the germanium out here by about 1200. And we saw that also get bright as well. Okay, so that's what we can do here. This helps us to identify core loss edges if maybe we're not sure of where they happen to be. Okay, all right. So now what we can do here is let me make this box smaller. So we're just isolating layers here, and we'll get rid of the slice tool there. And so starting from the top, now I'm going to actually go to the scan window and I'm going to bump my gamma up. So this is the carbon layer. So if we know where the carbon edge is, we can actually just expand this till we see it. And then, because there it is, right? It's at 2. If you're not sure where it is, you can come over here to the periodic table and you can click on all of these and it will tell you, and you can add them here manually. This is another way to do this. I'm going to show you how to do it by clicking on the spectrum though. So we'll just click cancel for now, and then I'll clear that. So now if you right click on the edge and then add to quant, there we go. There's a little bit of an oxygen one there, but it's going to be much stronger there. Okay, so I'm going to drag this over some more, right click, add to quant, oxygen, and now there's the silicon epi layer. So now way back here, okay, here's my silicon, okay, so that's already, you can see how that's much stronger than the other ones because of the amount of silicon, but also because of the cross section for this core loss edge. All right, display, home display, and then the last thing is the SIGI. Okay, so now the germanium core loss edge is going to be really weak, but we can see it down here around 1200. Left click, add to quant, germanium L. Okay, so that's how you identify your edges. Now, with this germanium, let me turn off the gamma here. Okay, with this SIGI layer, if we wanted to do a quant on the SIGI layer specifically, okay, so we want to sum as many pixels as possible, although we don't want to make this too wide vertically because then, you know, this interface is not perfectly flat, right? And we don't want to be, you know, we don't want to undersample, but we also don't want to oversample and hit, you know, the silicon, okay, because that's going to make our silicon higher than it probably is. So anyways, we're just going to quantify silicon and germanium in the SIGI layer. So let's get rid of the carbon. Let's get rid of the oxygen. And then what we can do now is we can go to the edge setup here, and we can see how it is doing the quant, okay? So what we see here, it's going to take us to the first core loss edge for the silicon, okay? So it's telling us, first of all, if you did DualEELS, which you should if you could, you always want to include pleural scattering, okay? The fit to the data is just much better. You have the ability here to change the threshold energy. Usually the default's pretty good. You shouldn't have to usually tweak this by more than a few EV if necessary. So the default was perfectly fine, so I'll leave that alone. If you're doing quant, you want to exclude the LNES, okay? Because you can see if I don't, then it's not modeled very well, okay? And there's plenty of signal in this core loss edge anyway. And then this is the range that it's using to fit the data. So what's happening before the core loss edge is really like where the background is coming from, okay? So you can adjust this to, you know, if it doesn't look like it's fitting well, like this, there's kind of a dip here. This is kind of tricky with this core loss edge because it's fairly low energy. So we're going to get some confounding possibly from the low loss features of the spectrum, the Plasmon scattering. So it may help to actually make the window a little tighter and closer to the core loss edge. So we'll leave that there. And then we'll go to the germanium. And same thing here. So I'm going to drag this window a little closer. Now you can see what's happening here, right? I'm getting more germanium under when I make the background window a little smaller, okay? So, but it looks like to me anyway. Now, if you mess this up, just hit the arrow here, the cycle, and that will put it back, okay? But it looks like this is a better fit to me if I make this a little bit smaller, okay? So we'll leave that there. And then if we want to save this for a future quant, we can. So go to the little disk here. I'm going to delete that, and I'll save a new one and just call it Siggy Quant. Okay, there we go. So then we can open it up. So now, if we want the quantitative result, we just hit quant. Okay, let me minimize this. And we can see down here in the output. So it's telling us which element, which shell, what the signal was, and the composition with some error bars. And it also is giving us areal and volumetric density, which we can do if we included the low loss data, which we have in this case. And it's also telling us the calculated inelastic cross section. So you can see for the silicon, it's about an order of magnitude higher than a germanium, which is consistent with what we're seeing in the data. Of course, part of that also is due to there being just less germanium in general, but that silicon cross section is very large, mainly because it's quite low energy. Okay, so that's the quantitative result. Now, what I wanted to see, because I wasn't sure before, was when I look at this, I'm not sure. We told it to exclude the LNES, so I'm going to do another quant here. Actually, scan, and I can just, oops, I need to draw a spectrum first, so click and drag. And I can just load this now. There we go. Okay, but what I'm going to do is I'm going to include the LNES now, and I want to see if we get a different result here. Okay, we'll click quant. Okay, so yeah, so the signal went up for both of those, as we would expect. You see here, yeah, so the signal went up for both of them, and so the quantitative results are not a whole lot different, actually, which is kind of interesting. So they're a little bit different, but it's not as significant as I thought. So yeah, so what it's showing in this window, it's actually not showing that it excluded the LNES, which was what I just wanted to verify. But yeah, you can actually see here, right, how it doesn't fit this as accurately. So that's again why you want to exclude the LNES usually with that. So just wanted to check and make sure. And so it actually was excluding it in the first result. Okay. All right. So what we can do now, though, is we can add back in the other elements, and we can now talk about actually mapping. Okay. So we'll go back to the high loss. So we have all of these. Now I want to just check again. So open up the edge setup here, and I need to, of course, scan, draw a picker. Where did it go? Nope, I guess I have to load those again. Okay, well, that's fine. All right, so actually what I can do, it is showing these. Because I don't know what I did with the germanium and the silicon. So actually I'm going to clear these, and I'm going to open up this one, and I'm going to add in the carbon and oxygen to those. Like we saw earlier. Okay, and I'm going to save this now. So this will be YouTube tutorial. Okay, and so we can check some of these other edges here just to make sure. Okay, so there's your edge setup. So we'll start with the silicon here. And what we want to see here, actually I should have not minimized that other window. Okay, so we're checking as we move along here that the background subtraction is working well everywhere. Now what's interesting with this is, for some reason, I'm seeing some silicon up in the carbon. I don't know why that's happening, but that looks real to me. So I thought this might have been a low loss feature, but I don't think that's what it is. I think that actually, because it looks very similar, right? What's going on up here. So I'm gonna assume that's real, even though I can't quite explain it at the time, but we'll leave that alone. Everything else seems to be working okay. We'll go to the carbon now. Now, depending on how well separated the edges are, you can tell it to include overlap or not. It really kind of depends here. So in the case of the carbon, it's doing what we want it to, right? So we're not seeing any carbon except where we're hoping to see it. So really, we don't need to include that. We should be fine not including any overlap. Same thing with the oxygen. We can include that as an overlap with the carbon, but since we only see oxygen where we expect it to see, right, there should be some in the carbon, the oxide, of course, and then not in the epi layers. This is perfectly fine, so we don't need to do anything there. And then, of course, we already did the germanium previously here. All right. So if that is all fine and good, we can go ahead and generate some maps. So we're going to click Map. And we're going to start by just doing a signal integral, and we'll display on a new workspace. I'll close the output window here. Okay, and then if you go to color mix, we can do a mixing of the colors. Now, it is, you have to be careful with how it displays these, okay? So one thing, I'm going to change the color of this guy, Control D, color. And this is custom, so there's no way to change this. We're going to have to change it in the color mix panel. Okay, that's fine. We'll leave that alone here. Actually, you can save this. You can save this as yellow. And we can probably do the same thing here. We can save this as blue. And we can save this as red. And we can save this as green. Okay, anyways, what I wanted to show you here is how it's assigning the contrast limit. So if you click on your image over here in display control, you can do auto survey, and that applies a histogram stretch. If you do Control D, okay, it may be clipping some of the data though. So you can see it is doing a little bit of that here. If we do a Control H for the histogram, you can see there's a lot of black pixels here. So, this is what we would expect, but we're not seeing like a nice Gaussian distribution. We're seeing something Gaussian up here, okay? Okay, so anyways, we'll close that. Do auto survey, do the same thing here, do auto survey, then do auto survey here. And now you want to do that before you do the color mix, okay? And then, so this ensures the maps all have equal brightness. You can do color mix, add all these, do okay. And now here's where we can change the color. So I'm actually going to leave this on, what I had been doing was putting this on magenta. It looks okay now, but actually, well, I'll leave it on this now because I know when we do it later for the atomic, like it doesn't work quite as well on magenta, but we'll leave it on magenta here for the time being. Well, since we need to do the yellow before, no, I want to do that actually, and I'll show why in a second. All right, and then to recolorize these, just click SRC. Now here, I can save this color map here. This is magenta. Okay, so now I have a bunch of saved color maps here. Okay, and then you can do Control L, and there you go. Okay, so we can now evaluate the maps. So do they make sense? So are we seeing what we want to see where we want to see them? And by and large, yes. Okay, everything looks how we want it to look. We're seeing a little bit of speckling with the germanium, again, because there's not much there. That's a high energy loss or a high energy core loss edge. So these tend to be a little noisier in general. But everything looks as expected. Actually, the silicon is pretty cool because you can actually see, I don't know how well you can see that, but that is atomically resolved. So pretty neat. Okay. So again, this is signal, right? And they're all, they've all been stretched, right, to give a equal brightness. Okay. So this is not really indicative of the relative amounts. So let's actually, instead of that, or before we do that, so one thing I would like to point out here is that how you set up the edge, the edge setup can be really important in your results or the maps. So actually, to show this, I want to show, let's assume that we're accounting for the silicon overlapping the carbon, and let's also assume that the oxygen is overlapping the carbon. Okay, so the carbon overlaps the silicon and the oxygen overlaps the carbon. Okay, and we'll go ahead and we'll generate the same map we just did on a new workspace. So we can actually change the names of these workspaces, and I'll show you how to do that, which is very simple to do and very useful. Okay, so we'll call it with overlap, no overlap. Okay, so with the overlap, I don't know how well you can see that, but we're starting to see a carbon signal in the silicon epi layer and the substrate, which is good. And we're also seeing a more pronounced oxygen signal in the silicon epi layer and substrate. Okay, so this has introduced some artifacts. Okay, so you have to be careful with this with your edge setup. If the edges are well separated like that, you really probably don't need to include the overlap. That's only when they're like really kind of tight and on top of each other. So, but we verified as we moved the picker across the layers, right, that everything was as it should and the background was being subtracted well, and so we really didn't need to include any overlap. But I did want to show that, okay, the importance of doing that. So let me go ahead and click close. We'll come back here, and I'm going to load the tutorial, and that gets rid of the overlaps there. All right, so let's talk about the other maps here. So we're going to do map. Actually, let me change this. Let me change this signal. I'm just going to call this signal. And let's generate now a signal integral, but it's scaled by cross-section. So in this case, right, it's going to do basically a histogram stretch. The maps are going to look basically identical to what we saw for just the signal, okay? So we'll call it signal scaled. Okay, so again, you can do auto survey. Okay, but now this isn't really useful. If we do the color mix, it's gonna look like, you can see these look basically the same as what we're seeing here. Okay, so this isn't really useful. What we have to do here is we have to change the contrast limits for each of these maps to be the same. Okay, so actually when you take the signal and you scale it by cross section, this is the precursor to doing an atomic percent map. Okay, so again, you can come to each map, analysis, stats, min, max. We'll do this for all of the maps. So what we see here is it looks like the carbon K has the largest value at 24.62. So we're going to set the contrast limits of every map to be 0 to 24.62. Okay, so you can see this is clipping some of the data with the carbon. Okay, so you're going to, now you want to uncheck auto survey here. No, uncheck. Do the same thing here. Check. Okay, so that got a lot darker. And then we would need to make this 0. Did I make it 0 for the oxygen? Let me make sure. I did. Okay. And then we'll do the same thing for the germanium. So this is going to get a lot weaker. Okay, so you can see what happened, right? That basically kind of went away. Let me close this, and we can do the color mix now. Okay, colorize these. Now here's where I found that this was easier to see actually with the yellow here rather than the magenta. So if I put this on the magenta, you can see that doesn't really show up quite as well. You could try some other things like this gray. And not really. I mean, again, it's very weak there. So yeah, I found that the yellow or the maize, the Michigan man that I am, that actually came out the best was to do that in that case. And again, you can play around with some of the other ways that we're doing this. The carbon isn't overlapped with anything. So if we put, for instance, if we make this red, let's say we make it red. Yeah, that really doesn't help either. So, okay, we'll just leave it on maize there. And there we go. All right, and then the last map I want to do is the atomic fraction. So from here, map, and then elemental composition. We can do these areal density ones. I'm going to skip that for the moment here, but you can do those too. So now with each of these, the scaling needs to be 0 to 100%. Okay, because again, if we just do auto survey for these, they're going to have the same brightness and it's not going to look any different. Okay, so atomic percent. So right click. Okay, 0 to 100. 0 to 100. That's already 0 to 100. And 0 to 100. All right, and then same thing. We'll color mix all of these. Do SRC and we can see, okay? So there we go. So this is how to properly show a percent composition map. You notice also no vacuum in here, right? You don't want to do one of these maps if you're over vacuum, okay? Because you're going to get fishy results because your spectrum is going to be just noise or just a ZLP, okay? So if you're going to do atomic percent, make sure there's no vacuum. The scaled signal and the signal will be resistant to that, so there's no issue there. But with the atomic percent, you want to avoid doing this where you have holes, okay? Or any kind of porosity or any kind of vacuum. All right, so the last thing here I wanted to show you, and we made it all the way through this so far, so we're doing good, is actually now extracting line scan from this, okay? So that can be very useful when you have these layer structures like this, which run horizontally, and we have, nice and flat from left to right. So if we want to do that, I believe we have to be in either the low loss or high loss. So let's go to high loss here and right click and profile. And if you click and drag and if you hold shift, that will keep. And it's going to pull up now. So whatever this, since we're in high loss, this is the high loss signal for the window. Let me do auto arrange here. Let me minimize that and do auto arrange. Okay, and then I'm going to scroll in to make sure that I have my okay. All right, now this is just 1 pixel up and down, okay? So pretty noisy. So what we can do is we can integrate or average from left to right, okay? So if you find control here, and then this W, you can integrate. And ideally, because now if your layers have a lot of undulation, these are relatively flat, so this is going to work well. But if they had a lot of roughness, then that's obviously going to be reflected in your final result, and it's not going to be probably quite as accurate. Okay, change the control to the middle here. I'm going to move it over here. Okay, there we go. All right, and so now to extract the line scan, you're going to right click on the edge of the box there, which is kind of tricky, and extract line scan spectrum image. And here we go. So I'm going to go ahead and minimize this. I'm going to delete that. Cancel, I held down Alt. There we go. Okay, so now doing this is the same as what we did before, okay? Everything still applies. It's a little differently though, because now you're looking at, this is just a line scan effectively now, and this is the HADF average line scan across the interface here. So if I want to see the integrated spectrum over a snippet of this, right, if I hold control, so this would be from the SIGI layer right here, okay? This would be from the carbon, this would be from the oxygen, right? This is the top of the sample, this is the bottom of the sample, okay? It's a little easier to do this on the scan window than it is on the low loss or the high loss, because now your vertical direction here is the line scan direction, and then you have an energy axis going from left to right. So if you do this on the scan and you know what these features correspond to, it's just a little more straightforward in my opinion, okay? And same idea as before, right? So if we want to map the core loss edges and do line scans, we can. So we already have these already here populated. Otherwise, we can, add them from the right. So again, we can right click on this, add quant, nice same thing as we did before. Okay, it's no different. All right, so let's go ahead and we'll do a map. And it's going to ask us to assign low loss, which we do. And we do want to assign that permanently. All right, so we'll create this on, we'll do the same display here. We'll stack the line scans and we'll do signal integral scaled by cross section and the atomic percent as well. Okay, and I'm going to do one more here. That's just signal integral. Keep. Okay, let me minimize this. All right, so here's our three. So this is the signal scaled by cross section. This is the atomic percent, and this is the signal without any scaling. Okay, so the signal without any scaling is kind of the least useful here because, again, right, it's not accounting for the fact that the cross section for the silicon is much bigger than it is for the germanium, and right, so this tends to be not too useful. So we'll go ahead and get that. The ones that scale by cross section, these are far more useful here. Okay. Again, these are the precursor to atomic percent, right? So in an atomic percent, the sum of the parts has to equal 100, okay? So basically that's what it's doing. It's very similar, I believe, to the quant for EDS once you have this scaled, the signal scaled by cross-section, okay? I believe it's very similar at that point, but there might be additional nuance on that. So a little less familiar with quantitative EDS. Okay, so, and we see what we would expect here, right? So we see the SIGI layer here well defined. We see only silicon in the substrate and then the epi layer. We see the oxide. We see the carbon layer, and we see some oxygen in the carbon, which we know again that why we're seeing silicon in the carbon though. That's the odd thing, but again, it looks like it's there. So I'm not entirely sure what to make of that. So last thing I want to show you is it's a little bit of a pain to actually get the raw data here. So let me minimize this one, and we'll do this with the percent composition. So what you have to do here, unfortunately, if you save this right now, so you do have the option if you save as, okay, so you can save it as a text or as an EMSA, but it's only going to save right now the carbon information, okay? So what we have to do is we have to isolate these, okay? So what you can do then, now I actually have a script here to extract the raw data, okay? But again, it's only going to extract the activated slice here, okay? So if you right click on this and you go send slice to back, okay? And I'll show you where you can get this script, okay? Otherwise, what you have to do is this, right? Go save and then save as, and then you can save it as, you know, text or as EMSA. But if you have this script, you can go to display, extract raw data, and it's pulling this up here, okay? So this is, actually, I'm gonna, I don't know why it does this for the carbon, but let me close this for a minute here, and let me send oxygen to the back, and now let me do that for this. Yes, so now this is the oxygen, and you want to save this as .txt, okay? Then you can open it as a text, and it's just literally 2 columns of data. Okay, and then we'll do silicon, send to back. Again, I don't know if there's a way to do this where it does all of them at once. That would be really nice. I think there probably is, but I don't know what that is at the moment. Okay, there's the germanium. And then for some reason, it doesn't do this with the carbon, but in terms of actually naming it, but that's fine. Okay, so it's just, this is carbon K percent composition .txt. So now if we actually open up these so you can see them, so you're, you know, seeing is believing, so they stay. Right, germanium, 0, 0, and then we hit the SIGI layer, and there you go, okay? If we do the same thing with the silicon, right, low, low, hit the epi layer, SIGI, and then we hit the substrate. And then we'll look at the carbon as well, since that was the kind of fishy one. And so we see it's high on the surface with the carbon, and then it drops when we get to the SiOx layer, and then it's non-existent in the epi layers. So just as we would expect. Okay, so I think at long last, I was able to cover everything I wanted to cover here with this tutorial finally. So thank you for bearing with me, and happy start of March, and good luck with your microscopy, and I hope to get more videos out to you shortly here. So thank you as always for all your support as we close in on 5,000 subscribers. Unbelievable milestone for me, and again, thank you so much for all of your support, and have a good evening.